All right, let's talk about something that I know can sound a little scary. Calculus. But seriously, forget all that. We're going to peel back all the complicated layers today and show you the simple, elegant blueprint that holds the whole thing together.
I mean, just think about it for a second. How do you actually measure a world that's always moving? You've got the speed of a falling apple, a satellite whipping around the Earth, the crazy ups and downs of the stock market. Nothing ever just sits still. And that question, right there, that's why we have calculus. It's the tool we invented to make sense of a world that refuses to stop changing.
So, what is calculus really? Well, at its heart, it's basically two big ideas. First, you've got the study of how things change in a single instant. Think of it like looking at a curving road and figuring out exactly how steep it is at one specific point. That's one half. The other half is about adding things up. It's like taking that curve and adding up all the tiny little slices underneath it to find the total area. It's the study of change and then adding up all those little changes.
And listen, this is not just some dusty old theory for a textbook. Nope. One of the first huge wins for calculus was predicting when Halley's Comet would come back. And today, it's everywhere. We use it to model how populations grow, to build economic forecasts, to understand the stock market. I mean, it's the backbone of modern physics and medicine. It is, and this is no exaggeration, the hidden engine that makes so much of our modern world run.
Okay, so that's the big picture. But how do we actually get there? How do we build something so powerful? You might think we'd have to dive right into these super complex equations, but that's not it at all. The real secret, the genius of it, is in its foundations. It's all about the simple, solid ideas it's built on.
And here's the crazy part. To understand a world that's always changing,
You actually have to start with things that don't change. It sounds like a riddle, right? But that's the secret. Before we can even start to talk about motion and change, we need to get on the same page about the fundamental, rock-solid building blocks of math, the things that are always true. So let's start with building block number one, the idea of a set. The best way to think about it is like this. Sets are the basic alphabet, the vocabulary of all of mathematics. You can't write a novel without knowing your letters, and you can't do calculus without understanding sets. Now, a set is just a collection of objects. Simple enough. But the key phrase here is well-defined. That's the important part. It just means you have to be able to tell with absolute certainty if something is in the set or not. The dictionary example is perfect. A word is either in the dictionary or it isn't. There's no maybe. The guy we have to thank for this is the German mathematician George Cantor. And what he did was huge. By creating this formal language of sets, he basically gave mathematics a solid floor to stand on. It got rid of all the fuzziness and paradoxes so that mathematicians could build these incredible, towering ideas without worrying that the whole thing would just crumble. It really is the bedrock. Okay, so we've got our language down with sets. Now for the next big piece of the puzzle. And this one required mathematicians to break a rule they thought was unbreakable for literally centuries.
So what is the square root of -1? Seems like a simple question, right? But it was a huge problem. I mean, you remember from school, a negative times a negative is a positive. So how on earth could you multiply any number by itself and get a negative result? With the numbers we're used to, the ones on a number line, you just can't. It's impossible.
And for hundreds of years, that was the answer. Impossible. Can't be done. Mathematicians were totally stuck. And it wasn't because they weren't smart enough. It was because their tool, the number system they were using, just wasn't up to the job. To get past this wall, they didn't just need a new idea, they needed a whole new kind of number. So along comes this 16th century mathematician, Girolamo Cardano, and he's working on solving these really practical real-world equations. And he has this wild idea. He thought, what if I just pretend I can take the square root of a negative number just for a few steps? And you know what? It worked. He found that by using these so-called imaginary numbers as a temporary step, he could get to the right real-world answers. They might have seemed imaginary, but man, were they useful. And that idea led to what we now call a complex number. It was like mathematicians collectively said, you know what, fine, let's just create a new number. We'll call it I, and its whole job is to be the square root of -1. And when they combined this new number I with all the regular, real numbers, they built a brand new, way more powerful number system. And just like that, what was once impossible wasn't anymore.
Okay, so let's recap. We have sets, which give us a rock-solid language, and we have complex numbers, which give us a number system that can handle anything we throw at it. Now we have solid ground to stand on. Now we can finally lay out the full blueprint for calculus.
So here it is, the whole roadmap. Step 1, that's the foundation we just talked about. Sets, functions, complex numbers. Then comes step 2, the idea of a limit. This is a really cool concept about getting closer and closer and closer to something without ever actually touching it. That one idea is the key that unlocks step 3, the derivative, which is our tool for measuring change at a single instant. And finally, step 4 is the integral. It's basically the reverse of the derivative. It lets us add up all those infinite little changes to see the total, the big picture. You see how it all connects? Each step builds perfectly on the one before it.
And that right there is the big idea I want you to walk away with. Calculus isn't some scary, impossible fortress of rules. It's more like a beautiful piece of architecture. It's this powerful machine for understanding how the world works, and it was built piece by piece on ideas that are actually pretty simple and logical.
So, let me leave you with this question. The next time you see the stock market jump or watch a comet streak across the sky, what are you going to see? Is it just random, chaotic motion? Or will you see what's really there? A world built on a hidden, elegant, and predictable blueprint.